All right, welcome back. We've got this optional video here where I just want to talk a little bit about the weirdness of what we're doing with determinants. There's layers to it that you're probably not used to in other math classes, but I think it's interesting, and you could totally skip this video and still do perfectly great in the class. But if you think determinants are weird, this might help you with that feeling because I think they're weird too, and we can talk about it. So, what we've done throughout this chapter is sort of implicitly assume that we have a function that we just call det that satisfies the definition properties of the determinant. We have not actually found a formula for such a function. We're just saying, like, signed volume should probably work this way. So these should describe properties of a function that calculates volume. Now, we have ways of calculating it by, like, using the scaling property and the column multiplacement property and the anti-symmetry property to do column swaps. So, and we know we can do these column operations to get something that is a triangular matrix. Like, we have an intuition for why that probably works. Haven't really proved that it always works, but it seems to work. Now, how do we know that that is actually a function that always gives you the same result? And how do we know that there isn't more than one function that makes that work? Like, for example, I just took one of the homework problems here, this matrix here. Let's call this matrix A. And I did some column operations to get a triangular matrix, and the product of the columns ends up being -8. So the question is, how do we know that somebody else couldn't have done some other sequence of column operations and eventually gotten something totally different, like, I don't know, 7? Because if that were possible, then the determinant of A would be equal to two different things, which is not a function. A function whose codomain is the set of real numbers needs to give you just a unique real number. You can't get two different things. So that would be not a function. Or what if there are, like, two different functions that are determinants? So, like, f and g both satisfy the definition of a determinant, but they give different outputs for some matrices. Like, maybe we can see how it works in R3. In R3, we know that if we have any given parallelepiped or parallelogram in R2, the volume of such a thing makes sense in a way. Like, we know there's no two different ways to calculate the volume of this thing using properties of, like, what a volume function should have. But how do we know the same thing is true in, like, R12? Like, what if you take f of b, and b is like some 12 by 12 matrix, and you get, I don't know, 20, and then you do g of b and you get something different. So that would mean there isn't a unique function that describes the determinant. Because maybe in R12, our concept of volume doesn't really have the same properties. There are a lot of things that are different about R12 and R3. There are things that are different about R2 and R3. Like, for example, in R2, if you take a smooth, closed curve that doesn't intersect itself, you know in R2 that is going to divide R2 into an inside and an outside region. And you can't get from one to the other without crossing the boundary, without crossing the curve. That's not true in R3. In R3, if you just have, like, a loop in the air and space, that doesn't separate R3 into anything. So maybe these properties that we're describing about how the signed volume of parallelograms and parallelepipeds work, maybe these properties don't actually work in R12. We haven't proven that there exists a determinant function, and we haven't shown that it is unique. So that is what I'm saying essentially theorem 3.10 is. Well, at least that a function that satisfies the definition of the determinant exists. And this is proved in an excellent book, Linear Algebra Done Wrong by Sergei Trail, which inspired my book's whole approach to determinants. We can sort of look at it here. This basically says that the determinant must be defined by this function, and this function is done in terms of permutations, which is a little bit beyond this class, but you might be able to read it. So if you feel like you're up to it, you want a little challenge, and you have a couple hours, I would recommend reading this part of Linear Algebra Done Wrong. It's a free textbook. You can download it from the internets. Maybe that should be like an extra credit assignment. Maybe if you like read this section of this book and demonstrate to me somehow, maybe by doing some exercises from it, that you understood the proof, I'll give you a few extra credit points. So yeah, it turns out it exists, and based on the fact that it exists, we can use what theorem 3.11 says. This says, suppose that there is a function, then we basically say that this is the formula for it. And that also means the determinant is unique because this is a formula for it. So if there is a determinant function, which the Sergei Trail book proves, in the textbook, I have a proof of this part, that at least this is a formula for it. And if you want to read that, maybe that should be extra credit too. Anyways, we'll talk about this cofactor expansion in a lot more detail in the next video. So I'll see you then.